Hello everyone, myself Rajale Samsundar. My subject is mathematics. In today's lecture we go with the concept of the chapter matrices. Previous lecture or in the first lecture of the matrices we see what is the elementary transformation. We know there are 6 elementary transformations, 3 is for rows and 3 for columns. Okay, in today's lecture we go with the concept of the inverse of matrix. Inverse of matrix. This is the very interesting concept in this chapter. Here we consider the square matrix. Okay, let us consider example. Here A is the matrix having 2, 1, 4, 2. Everyone knows this matrix is having 2 rows and 2 columns. So this matrix is having order 2 by 2. Okay, so here given matrix is a square matrix. Then consider another one. Here B is the another matrix and is having here 1, 0, 0, then 0, 1, 0, then 0, 2, 3. Okay, here again in this matrix we have 3 rows and 3 columns. So order for this matrix is 3 by 3. So this is the matrix and having the order 3 and is square matrix. Here we only define the inverse of a matrix of a square matrix. To find the inverse we consider only the square matrix. Okay, so remember this thing. Let A is the given matrix having the order M. Okay, then we consider another matrix B. Here B is the matrix having order M again. That is, here A and B both are having the same order and both are the square matrix. Then we consider one relation here. AB, that is product of matrix A and B, is equal to product of matrix B and A if the product of BAB or here product of BA is identity matrix. Remember this thing. If product of AB is a identity matrix, then here product of BA is also identity matrix, then we say here B is the inverse. Here B is the inverse of matrix A. Remember this thing. Very important. I repeat again. Here we consider only one relation AB is equal to I. If this product is identity matrix, then here this B is called the inverse of matrix A. Inverse of matrix A. Okay, similarly here again we define this B for inverse of matrix A. Okay, if we replace this B by using our A inverse, remember again we consider the same relation. If we replace this B by using the A inverse, then we get a form here A inverse is equal to A inverse A and is equal to identity matrix, and by using this concept we find inverse of matrix A. By using the same concept, A inverse is equal to A inverse A is equal to I. Using this concept we find inverse of matrix A. Okay, let's go with our first thing. Let's go with our first thing here. If determinant of A is not equal to 0, remember if determinant of A, we consider this matrix, we consider determinant for the same matrix, okay, and we denote this by using this symbol determinant of A. If this determinant of A is not equal to 0, then we say here A inverse exists. We say here A inverse exists. Remember, if we have determinant of A is equal to 0, then inverse of matrix A does not exist. It does not exist. So remember this thing. Okay, so using this point also we find the inverse, or we say inverse of given matrix is exist or not. We check this by using this relation. Okay, now we have to consider the uniqueness, that is uniqueness of inverse of matrix. Uniqueness of inverse of matrix, that is inverse of matrix is unique or not. We have to check this, and to check this we consider one theorem. Here statement is having prove that if A is a square matrix, then its inverse exists, and is unique. Okay, that is inverse of a matrix A is unique. Let's go with our proof. Let us consider A is the given matrix and is a square matrix. Let A is a square matrix. We also consider the inverse of matrix A is exist. Consider inverse of matrix is exist. Okay, consider B and C are the inverse of given matrix A. Let B and C are inverse of matrix A. Okay, if B and C are the inverse of the given matrix, then we consider the relation. Here AB is equal to BA and is equal to identity matrix. That is product of AB is I. That is product of this BA is also I. Similarly for the matrix C, we define the relation. Here AC is equal to CA and is equal to identity matrix. This is by using the definition of inverse of matrix. Okay, now to define the uniqueness. We consider one relation. Okay, now consider here B is equal to BI. Now here remember this matrix B into any matrix B into identity matrix I is always B, having the same order. If we have a C, we define C is equal to Ci, that is product of this C, matrix C, and this identity matrix is again C. This is very important relation. Okay, and using this relation we have to prove this uniqueness. Okay, here I write B as it is equal to, now here B as it is. Now we consider this I. We replace this I by using the AC. We know here AC is I, so we replace I by using AC. Now this is equal to, here I write this as BA into C. Okay, now this is equal to, we know this product of matrix B and A is again I, so we replace this BA by using I, so IC, And lastly, here we get B is equal to C only. Here we get B is equal to C only. So we say here B and C are same. येथे B आणि C हे दोन्हीही सारखेच आहेत. So here inverse of matrix A is unique. Okay. So here I write, therefore the inverse is unique. The inverse is unique. So remember this theorem. This theorem is also very important. Okay, every matrix A has the unique inverse. Matrix A is having the unique inverse. So we prove this by using this relation, by using our definition of inverse of matrix. Okay, so this is very simple concept. Now we consider the concept of inverse of matrix by using elementary transformation, that is by using our 6 operation. Okay, so here inverse of non-singular matrix, inverse of non-singular matrix, singular matrix by elementary transformation, by elementary transformation. Okay, this is the very interesting concept. We have to follow the operations, 6 operations in that 3 is for rows and 3 is for columns. Okay, again to define this concept, we consider a relation. Okay, here A inverse is equal to A inverse A and is equal to identity matrix. Using this relation we find inverse, and to find the inverse, remember here we have to convert this matrix A. We have to convert this matrix A into identity matrix. Okay, and we perform some row operations or column operation, that is row transformation and here column transformation to convert this. Okay, we use operations on both the sides. Remember here in A inverse is equal to I, we perform operation only on our prefactor A. We perform operation on only prefactor A, not on this A inverse. Not on this A inverse. Again, in RHS, we perform the same operation. We perform the same elementary operation. Okay, I repeat again, we perform the elementary transformation only on this matrix A and this identity matrix, and not on this A inverse. Not on this A inverse. Remember this thing. Okay, let's go with our row transformation. Okay, so here if we have to use row transformation, then we consider here A inverse is equal to I, and if we have to perform the column transformation, we consider the equation here A inverse A is equal to identity matrix. Remember, this is for row transformation, A inverse is equal to I, and for column transformation we consider A inverse A is equal to identity matrix. Now here, by using the elementary transformation, by using the row transformation, we convert this matrix A into identity matrix. Okay, and same operation, we apply the same operation on this identity matrix. So this identity matrix is converted to B, and we get the relation here IA inverse is equal to B. We know here identity matrix into any matrix is always our matrix. So here A inverse is equal to B. Okay. Then here for column transformation, we consider A inverse A is equal to I. That is, here we have to convert this A into identity matrix by using the column transformation. For the column transformation, we consider A inverse A is equal to I. Okay, we convert this matrix A into identity matrix by using the column transformation, and same transformation we apply on this identity matrix. So this identity matrix is converted into B, and we get here important relation, and is here A inverse I is equal to B. And using this, I write this as here A inverse is equal to B. A inverse is equal to B. So, in the same way, we find the inverse of another matrix. Okay? Let us consider some steps to find the inverse of matrix by using row transformation and by using the column transformation. Firstly, we go with the row transformation. Inverse of matrix by row transformation. By row transformation. Okay. To define this concept, we consider one matrix. Let us consider A is the given matrix. A is the given, and this matrix A is having elements here A11, A12. Then for second row we consider A21, then A22. We have to find inverse of this matrix A by using the row transformation. Since we have to use row transformation, we consider here A inverse is equal to I, that is identity matrix. Okay, and to find the inverse, we follow some steps, some important steps. Okay, here in step first. Okay, firstly consider the identity matrix. Here, if our given matrix is having order 2, then this identity matrix is also having order 2, and this identity matrix is like here in first row 1, 0, and in second row, for second row we consider 0, 1. That is, we have to convert this matrix A to this identity matrix. Okay, and to convert this, we go with our first step. In our first step, we reduce this A11 to 1. This A11 to 1, here reduce A11 to 1. Next step, in the second step, we reduce this A21. Reduce this A21 to this 0. Reduce A21 to 0. In the third step, we reduce this A22 to 1. Reduce A22 to 1. And in last, that is in fourth step, we reduce this A22 to 0. We reduce this A22 to 0. Reduce A22 to 0. And using these four steps, we find the inverse. Okay? So remember this thing also. If our matrix, or if our given matrix is having order 3, Then again we consider some steps. Let us consider matrix A having order 3. Here in first row we consider A11, then A12, next A13. Here for second row we consider A21, then A22, next here A23. Then for third row we consider elements A31, A32, A33. Remember one thing here, this A11 is in the first row and in first column. In first row and in first column. So we denote 1, 1. Similarly, here A12 is in the first row and in second column. So we consider this 1, 2. Next, here A13 is in first row and in third column. So we consider this A13, 1, 3. Similarly for each element. Here, if we consider this A32 is in third row and in second column. So here we consider this 3, 2. Remember this. Okay. Again, to find the inverse, we have to reduce this matrix A to identity matrix. Okay. And here identity matrix of order 3 is like here in first row 1, 0, 0. Then in second row 0, 1, 0. Then in third row we consider 0, 0, 1. Okay. So to convert these we consider some steps. Again in the first step we reduce this A11 to 1, reduce A11 to 1. Then in second step we reduce this A21 and A31 to 0, reduce A21 and A31 to 0. Next, here we reduce this A22 to 1, reduce A22 to 1. In fourth step, we reduce this A12 and A32 to 0, reduce A12 and A32 to 0. In fifth step, we reduce this A33 to 1, reduce A33 to 1. And in last step we reduce this A13 and A23 to 0, reduce A13 and A22 to 0. Using these steps we convert this A matrix into identity matrix, and this is for by using the row transformation, that is by using the series of row transformation. If we have to use column transformation, then we have some another steps. Okay, so we consider column transformation. Okay, inverse of matrix by column transformation. And in that, if we have to convert A into identity matrix, in that we consider relation. Here A inverse A is equal to identity matrix. Again, we convert this A into identity matrix by using the series of column transformation. Okay, so here we consider matrix A to define how to convert the given matrix into identity matrix. Here if we have A and this A is having here A11, A12, next A21, A22. Okay, to convert this into identity matrix like 1, 0, 0, 1, we follow some steps. Here in step first, we reduce this A11 to 1 first. Reduce A11 to 1. Next, now we reduce. In the step 2, we reduce this A12. Reduce A12 to 0. Then in third step, we consider this A22 and we have to reduce this A22 to 1. Reduce A22 to 1. And in last, that is in fourth step, we reduce last element, that is A21 to 0. And here we perform this series of column transformation to reduce this given matrix A into identity matrix. And this is for the matrix having order 2. Now we consider the matrix having order 3. Here if matrix A is having elements A11, A12, A13, then A21, A22, A23, then A31, A32, A33. Okay, total 9 elements. Again, to convert this matrix A into identity matrix, like here in first row 1 0 0, for second row 0 1 0, and for last row 0 0 1, we perform series of column transformations. Okay, and to reduce this, we consider first step. Firstly, we reduce this A11. Reduce A11 to 1. Then in second step, we reduce A12 and A13 to 0. Reduce A12 and A13 to 0. Next, we reduce A22. Reduce A22, that is middle element, to 1. In the fourth step, we consider A21 and A23. Okay, so reduce A21 and A23 to 0, like this. Next, in the fifth step, we reduce this A33 to 1, A33 to 1, and in the last step, we reduce this A31 and A32. Reduce A31 and A32 to 0. So by using these steps, by using this series of column transformation, we reduce this matrix A into identity matrix by using these steps. So in today's lecture, we see what is inverse of matrix. Then we consider uniqueness of inverse of matrix. In next step, we consider how to find or how to convert the given matrix A into identity matrix by using series of row transformation. We see some important steps. Then we consider how to convert given matrix A into identity matrix by using this series of column transformation. Again, we see these 6 steps. Okay, and using these steps, we consider the conversion. We do the conversion. Okay, in the next lecture, we consider some important example related with the inverse of matrix. Okay, thank you.